Hello, 7th graders, and welcome back to my YouTube channel. Today I want to talk about division theorem. Division theorem, it seems simple enough. As you can see, it's just simply a relationship of, think about division with remainders like you learned back in elementary school. If you can get into that mind frame, this is going to be relatively simple to see. That is to say, if I had 21 divided by 4 equals 5 remainder of 1, yeah, you probably did some math problems that, well, looked like that back in elementary school. We're going to call the dividend, this number right here, that's going to be a in this formula, while the divisor, that's this value right here, that's going to be the b, okay? And then our quotient, let's make it a nice purple there. This is our quotient, as you can see, and then, of course, our remainder. All right, so simply put, division theorem simply says that a equals b times q plus r, where a is going to be the number that's getting divided up. There exists exactly one pair of whole numbers, q and r, that are going to satisfy this condition as long as b is greater than 0. That's what the division theorem basically says. So it's so if I have like 50 divided by 11, yeah, it equals 4 remainder of 6, which is to say that 50 can be written as 50 equals, and I can write 11 times 4 plus, oops, I wrote 4, 6 I meant to say. There we go. So, and again, now you say, well, there's got to be a number of ways to write 50. Couldn't I just say 2 times 25, with the remainder of 0? Well, sure. But I'm looking for exactly one pair of whole numbers, and in this case, I'm talking about the 4 and 6 that are going to satisfy these conditions. That is to say, our remainder is actually less than the 11. Okay, so 4 and 6 are our two numbers here. The remainder, as we set up here, we said 0 is less than or equal to r, which is less than b. b, in this case, was the 11. There's going to be one remainder that's less than 11 that's going to fit this. So we're going to explore this a little more deeply here with some variable expressions. See, we got kind of wonky here in a hurry, didn't we? So consider, suppose a, b, q, and r are whole numbers such that a equals b, q plus r, like so. And again, we've got that r is something less than b, but it's greater than or equal to 0. So we can show that b is the divisor, and the dividend is a plus 3b, and then I'll have r as the remainder. And here's how that's going to work. Consider, I'm going to change up my colors here. All right, so we said that a equals bq plus r. So I'm just going to rewrite bq plus r instead of a. See what I did there? So there we go. And now that I have written this, I just kind of take this bq plus r plus 3b, and I use the associative property and commutative property to rewrite it as bq plus 3b plus r, but now that's in parentheses. So now I've got this b that I can factor out and say b times the quantity of q plus 3. So thus, I've shown it that that b is the divisor, the dividend is a plus 3b. See, like so. Because again, I've got that, I told you a belongs here. Show that b is the divisor and the dividend is a plus b, then r is the remainder. Okay, so again, if I write a plus b on this one, again, I'm just following this formula up here, right? So I'm replacing on this one, so a plus b is my dividend now. So I'm going to replace a with, I'll change up my colors here so you can see what I'm doing. A is now getting replaced with bq plus r, just like I had up here, right? See, bringing it down here. So now I've got bq plus r plus b, and again, I can utilize commutative and associative property to have bq plus b. I can now factor out b, and now I've got b as the as this divisor here, b divided by q plus 1 plus r. Show that where b is the divisor and the dividend is a minus 7b, then I'll have a remainder of r. So again, same kind of drill. I'm just replacing A with BQ plus R, like so. And so now I will group up, associative and commutative properties, BQ minus 7B, and I'll now factor out the B, and there I've got that Q minus 7 as the other factor for B. When I have A plus 100B as the dividend, you see where I'm going here? I mean, I'm just constantly just replacing A with BQ plus R, and then I'm rearranging the R and the 100B like so I can factor out the B like so. And so what this tells us, we have a nice general rule for this on this. A whole number A plus any multiple positive whole number B is going to leave the same remainder when divided by B as is left when A is divided by B. Same is true of A minus any multiple of B, which is such a multiple of B not greater than A. So some other things that we talk about in this particular unit here. We can show, you're asked to show, one of the proofs for every whole number n, the product of n times n plus 1 times n plus 2 must be some multiple of 3. Now, if it's a multiple of 3, so then I should be able to divide 3 into n like so. So n is 3x plus r, and x has got to be some whole number, and r has got to be a number 0, 1, or 2 according to the division theorem. Okay, fine. If r is equal to 0, well, that was easy. Then 3 times x had to be some multiple of 3. That's easy. But what if r is 1? Well, now in this case, I could add 2 on both sides of this here, like so. So if I have, I have n, because I said n plus 2 equals 3 times x plus 1 plus 2, because I'd have n equals 3x plus 1, because we're adding that remainder on, right? 3x plus 1, remember this, right? So then that I could regroup, the 1 plus 2 is obviously 3, of course. And now I'd have 3, let me write this with a pen here. So if I have 3x plus 3 like this, I can now factor out a 3. 3 times x plus 1. So there I go. I've clearly shown that I have some multiple of 3 that I factored out. When the remainder is 2, it's a similar thing. When the r is 2, then the n plus 1 factor can be shown to be a multiple of 3 using this technique. Again, I'm just factoring and regrouping. So yeah, when the remainder is 1, then n plus 2 is going to be the multiple of 3. When when r is 2, the remainder is 2, n plus 1 will be the multiple of 3. So yes, one of these 3 expressions has to be a multiple of 3. Therefore, when you multiply by any other 2 numbers, you have a multiple of 3, definitionally speaking. Then I can do a similar technique to show a multiple of 6. Now remember, to be a multiple of 6, it's got to be an even number that is also a multiple of 3. Now, in this case, we know that n times n plus 1 has to be a multiple of 2. It has to be, folks, because it's consecutive. One's odd, one's even. You always get an even number. So this has to be n times n plus 1 times 2n plus 1, regardless of what 2n plus 1 actually is. I must have some even product. Okay, moving on, we can state then that n equals 3x plus r, and just using the same technique as I had before, aren't I? So again, if r is 0, then n must be a multiple of 3. If the remainder is 1, I can show that the 2n plus 1 is a multiple of 3. And when r is 2, I can show the n plus 1 is a multiple of 3. And again, here's these factoring techniques. Again, in both, I color-coded it here to try to make it a little more apparent that the n and the 3x, n gets replaced with 3x plus 1, and then I'm able to factor out 3. And here, I replace n with 3x plus 2, and I'm once again able to factor out a 3. So in cases of all 3 numbers, n or n plus 1 or 2n plus 1, one of them must be some multiple of 3. Therefore, the product must always be a multiple of 3. And since I showed earlier it's a multiple of 2, it also has to be a multiple of 6. Okay, I hope that helps you as you're filling in the exercises up through 60. So you're starting on 54 through 60. Again, if you encounter these problems, feel free to reference back to these notes. We'll see everybody next week. At this point, I hope to be able to do a quiz sometime towards the end of next week. I don't have an exact date chosen yet, but sometime between Wednesday and Friday of next week. Thank you for listening. Hit that like button and be sure to subscribe to my channel. Be good for your parents and have a great